All right, hello and welcome back. So this is another ALEKS topic. It's called calculating the reaction rate of one reactant from that of another. And this is a really nice little review type topic. It's sort of also an introduction to kinetics and the stoichiometry of kinetics. So I think it's a good topic in that sense, but I also really like the review aspect. So in this video, I'm just going to talk about this one problem. So I'll go a little bit slower, but yeah, let's go ahead and get into it. The first part of this, most of the sulfur in the United States is chemically synthesized from hydrogen gas recovered from natural gas wells. In the first step of the synthesis, hydrogen sulfide gas is reacted with dioxin gas to produce gaseous sulfur dioxide and water. So from this sentence, we need to be able to pick out sort of the relevant pieces of information, so sulfur dioxide and water, and come up with a balanced chemical reaction from all of this information. So hydrogen sulfide, that's HS, dioxin gas, that's O2, sulfur dioxide is SO2, and water obviously is H2O. And the first thing that I'm going to do is actually just write out a chemical reaction. So initially, I'm not going to know what the coefficients are. I'm just writing out what the different chemical species are. So since it says these two things are reacted with one another, those are going to be my reactants. And these two things are produced, sulfur dioxide and water are produced, those are going to be my products. And then I would go through and balance the chemical reaction. If you're looking at this and you don't know, you're like, I don't know what hydrogen sulfide is, just look it up, right? You've got a way to figure that out. So go ahead and just Google hydrogen sulfide, you'll find that it's HS. So once you get to this point, then we need to balance this chemical reaction. Anytime we are dealing with the chemical reaction, we want to make sure that we're dealing with a balanced chemical reaction. So I'm not going to talk about how I came up with these numbers in this video, but obviously we do need to be able to balance chemical reactions at this stage if we're doing a problem like this. So this is really the starting point, right? So you need to take that information from that first paragraph, come up with a balanced chemical reaction that will govern the rest of the problem. So that's step one. Now it says, suppose a chemical engineer studying a new catalyst for this reaction finds that 264 liters per second of oxygen are consumed. So I'm just going to write 264 liters per second right underneath my oxygen. That's just the way that I like to organize my work, and I would encourage you to do the same when the reactions run at this temperature and this pressure. Then the question, calculate the rate at which sulfur dioxide is being produced, right? And this is something that a chemical engineer would want to know. They would want to know for this process, if we're going to be producing SO2, I want to know how much we're going to produce, right? So this is a very nice real world application here if you're going to become a chemical engineer. So the question that we're being asked is the kilograms per second for SO2. What's the mass per second of SO2 that will be produced? Obviously, because we want to know, how much we can sell. So we're going to be able to relate the rate at which O2 is being consumed to the rate at which SO2 is being produced. Now, what's important to notice from our balanced chemical reaction is that there's a 3-to-2 ratio between how often or how quickly the O2 is going to be consumed and how quickly the SO2 is going to be produced. For every 3 moles of O2, you're only going to form 2 moles of SO2, and we're going to need to take that into account sort of later on. Now, from this point, there's actually a number of different ways that we could go about solving for our final answer. I'm just going to walk you through the way that I did it, but again, there are different orders that you can do the next things that we're going to do. So the thing that I noticed when I was, got to this point of the problem, so I sort of, got here, took a step back, I see that we have a liters of volume of oxygen, and we're asked to find a kilograms of SO2. So when I see kilograms, of course, I think of moles. We're going to need to use, find what the moles of SO2 being produced to then convert that into kilograms. And I know that the ratio here, 2 to 3, is a mole to mole ratio. So then the question becomes, is there a way I can sort of relate the volume of O2 to the number of moles? And of course there is. PV equals nRT. We have an ideal gas law problem here. So in this problem, we are given a volume. So volume equals 264. We are given a temperature. Temperature equals 211 degrees Celsius, which is 484.15 Kelvin. So remember, in ideal gas law, we need to be using Kelvin. Our pressure is given as 0.55 atmospheres, and again, in the ideal gas law, that's good, that's what we want. So with this information, we can actually solve for the number of moles. So if we know that PV equals an RT, I'll do this over here, 0.55 atmospheres times 264 liters will equal some number of moles, times R, 0.08206, times the temperature, which is 484.15. Solve this for N, and we should get a value of 3.65 moles of O2. So that correlates to the volume of O2. So another way to say this is that 3.65 moles of O2 would be consumed every second. That's a lot, right? But if you think 264 liters per second, we're doing this on a large industrial scale. We're going to be forming a lot of or consuming a lot of O2 every second. So this is the number of moles of O2, and maybe we'll sort of annotate this. Consumed every second, right? So that's sort of from this information here. Now we need to relate this, rate of consumption of O2 to the rate of production of SO2, and that's just a multiple ratio. So if we know that we have 3.65 moles of O2, multiply that by 2 moles of SO2 will be produced every time we consume 3 moles of O2, then we should end up with 2.43 moles of SO2. And then this is going to be the number of moles of SO2 that are produced per second, right? So we always have to sort of keep in mind what the what the significance of our values are. So every second you will be producing 2.43 moles of SO2, but we want our answer in terms of kilograms per second. So basically at this point we just need to do a moles to grams conversion and convert this number of moles of SO2 first into kilograms and then into grams. So the way that I would do that, let's just drop this down, 2.43 moles of SO2 times 64.07 grams in every 1 mole is 155.7 grams of SO2. Again, produced every second. So, sort of following all the way through. This is the volume of O2 that's consumed every second. This is the moles of O2 that are consumed every second, multiple ratio. This is the moles of SO2 that are produced every second. And then I've converted that moles into grams, produced every second. And then finally, we want kilograms per second. So just converting this into kilograms would be 0.1 and then 2 sig figs, 16 kilograms per second of SO2. Make sure you can see that. Produced. So that's a lot of work, right, to get us to our final answer there. But that's what we're looking for: balanced chemical reaction, multiple ratios, stoichiometry, ideal gas law is thrown in there. So make sure you're understanding all of the aspects of this, sort of what each step is representing. So these little annotations I think are really good for this type of problem. But that's what we're looking for, 0.16 kilograms per second. All right, cheers.